Excellent. So now we're in a position to really just reflect a little bit again on verification. And so what I want to look at for today is really just comparing some of the finite element estimates for stress concentration factors versus what you did in MOW227 in terms of Shigley. And this is a nice example where we're going to be bringing a couple of things together in terms of the modeling. It will involve the usage of some consistent loading. That's something that you should be quite comfortable with now and understand quite well, as well as a nice illustration of where we can practically save computation if you look at this kind of model, asking the question whether we can exploit some symmetry to try and reduce the size of the model. Okay, and what we're going to look at is essentially what happens as we make a mesh finer. So we start off with a mesh that is going to be quite coarse, but it will run quick. Then it'll make it finer, and then it'll make it very fine. And as you'll see, it will have implications in terms of the computational time required. And so this is why it's important that we again consider meshing appropriately, and making sure that we use a mesh that is fine enough but not too fine. So that's sort of some of the take-homes here. But it's a nice example just to show you more or less those stress concentration factors that you were that was sort of supplied in Shigley in those tables or in those graphs that you had to read off, just to show you that the finite element method really naturally recovers what's going on in terms of if we have a stress concentration. So this is different from a singularity. So first of all, I just want to start off by saying singularity is typically we have an acute sharp angle that you essentially try to pry open, so put into some form of a tensile opening mode. That will result in infinite stress because of the fact that we're modeling it linear elastically. So if you keep on refining that at a singularity, your stress will go to infinite. It will just keep on climbing. A stress concentration is something different, in that there's no acute sharp angles or corners, anything involved here. This is just the fact that we have essentially a stress razor because of some kind of a circular hole inside another plate that gets sprayed open, that gets pulled open. That is essentially what we deal with the stress concentration. What I also want to make you aware of is, as we make the mesh finer, we'll start to represent this geometry better, because this is another aspect that is important to understand. Because we are using a mesh to describe the geometry, sometimes if the mesh is too coarse, our description of the geometry might still be poor. But as we make the mesh finer and finer, our description might improve drastically. So that's also something to just keep in mind when it comes to finite element modeling, that sometimes as you make the mesh finer, it's not only that the answer gets accurate because of the fact that you have more elements, it might also be that your geometrical description of the problem improves and gets more and more accurate. Okay, so hopefully this will give you just an idea of where we are. Okay, so take-homes really is a bit more complex finite element geometry, and really just do something that you've done quite extensively in MOW227, just to see for yourself that that the stresses that are sort of maximum pops out of the finite element method when modeled appropriately. Okay, so first off, let's recap quickly on the MOW227 knowledge. So this plate we have now thickness of 1 mm, that's just given, so 40 mm height, 20 mm diameter hole, 18 mm long, applying 2.5 meganewton per meter squared pull, so that's essentially 2.5 MPa that we apply. Alright, so that's what we start off with. If you recall from Shigley, your KT factor is essentially the ratio of the maximum stress versus the nominal stress, where your nominal is really the essentially the stress computed based on the cross-sectional area that's defined here. So it would be essentially the cross-sectional area of this plate minus the cross-sectional area of the hole. So that's really what's implied by the normal stress. And then your KT factor is computed based on some empirical relation, and you can go and compute it as 2.156. If you know what your nominal stress is, in this case, if you think the stress here over this edge is 2.5 MPa, but if I were to half the area, it would go up to 5 MPa. So you can go and compute 2.156 times essentially 5 would essentially get get you to the 10.78. Okay, so that's just broadly speaking how we more or less arrive at the 10.78 MPa. Because of the fact that we have essentially a couple of symmetries, so if you think about the problem, this is symmetrical. I can flip the bottom half across the top half and things stay symmetrical, and there's a symmetry plane here. I can flip things from the left to the right, and things also, the arrows fall on top of each other. Because the geometry, the material, everything is nice and symmetrical around this axis. I've got a symmetry plane in the vertically through the circle as well as horizontally through the circle. So I can really reduce this problem from this modeling, instead of modeling this full thing, to really just modeling this part here. And that is a big benefit, that we can save quite a lot of time. And so if you think about what kind of symmetries we have to, what kind of boundary conditions would be applied on each of these symmetry planes, we would just have to put rollers in. And you could just think of it also, imagine what will happen if you pull on this thing. There's no reason why this line would move up and down. Because of the symmetry, but it would want to move left and right. So this hole will become sort of an ellipse. You can just imagine that ellipse kind of thing. A lot of tension that we'll see here, so we expect to see some maximum stress there at the top as the thing gets pulled into that elliptical shape. Again, anything on this line, there's no reason for it to go left and right, because balance of the forces, but definitely up and down as this thing goes down. So you want to put rollers down here. So vertical rollers, allows vertical displacement here, and rollers allows for horizontal movement here. That's really what we need to do to be able to model this. Okay, so that's also your challenge. Go and take each of these measures and just estimate for yourself what the consistent node loading would look like, as well as what the boundary conditions essentially would look like. And you can also ask yourself, if we apply rollers like this and apply rollers like this, then there's no rigid body modes left. So this thing can't rotate. It can't move left, it can't move right, because of the rollers here would limit any horizontal movement, and rollers here would limit any vertical movement. And because we've got both rollers there, that limits rotation. So no rigid body modes. So that's something that would solve. Okay. So that's something that we can imagine now. So this is how it would look if you were to go and model this. Okay. So hopefully this gives you a good idea of where we are. Okay, so we just model sort of a quarter of that circle, and then this part here, and then the consistent node loading that we apply on